miscible like tert-butanol and water. They form two phases. You have some organic compound that's too water soluble. You want to extract it into the tert-butanol. You throw in a couple of fistfuls of salt. The salt goes into the water. It suppresses the solubility of the neutral organic compound in water. It transfers over to the butanol better, or ether, or what have you. You suck off the organic layer, blow it down, and you get your product. It's an extremely well-known process, salting out. A biochemist, biophysicist by the name of Hofmeister studied this quantitatively for lots of compounds, and he measured the effect of different salts on solubility in water, and got his name tacked on to this process. Even though this is ancient history, people are still really trying to understand why it happens, and I've seen papers as recently as last year in chemical physics journals on trying to understand the Hofmeister series. Okay, moving on. Temperature effect on retention. This is a log scale. So this is effectively a plot of the logarithm of K, the retention factor, versus 1 over T. That's 1 over T. So this is a Van 't Hoff plot. Plot of log of equilibrium constant versus 1 over T. Physical chemistry 1. Van 't Hoff plot. Straight line. The slope of the straight line is the enthalpy of the process. For neutral compounds, meaning uncharged molecules in reverse phase chromatography, the slope is almost always positive. What that means is that as we go to higher temperature, 1 over T is getting smaller in that direction. So as we go to higher temperature, we're coming that way, we get a decrease in retention factor as we increase temperature in reverse phase chromatography. It's not always so simple because ionic compounds frequently show the opposite trend, even in reverse phase chromatography. Generally, this is a very small, I shouldn't say very small effect because you're going to think it's negligible. It's not negligible. But typically, we're looking at about a 3-fold decrease in retention for about a 50 centigrade increase in temperature. That's a lot less than what we see in GC. Typically in GC, we see a 2-fold change in retention for maybe a 10-degree change, a 2-fold change in retention for a 10-degree change in temperature, maybe a 3-fold change for a 10-degree. So that's 10 versus 50. That's a big difference. Slope is much smaller. The slope is the enthalpy of the process. So if I calculate the slopes of this stuff, what the slope is delta H of retention divided by R. So if you got a small slope, you have a small delta H of retention. So why is it true? Go back to regular solution theory, think about it, and write me no more than 1 page with equations and cartoons. And if there's no cartoon, I'm not even going to read it. And explain to me why the effective temperature in reverse phase is so much smaller than effective temperature in GC. If you need more than 1 page, you don't understand it. But you need to understand this. All right. Changing gears enormously, we're going to talk about the effect of pH on retention. Neutral compounds, compounds that are not acidic or basic, you can change the pH and you will see essentially no change in their retention. If for instance we had a 10 millimolar pH 3 buffer and a 10 millimolar pH 5 buffer, there'd be no change in the retention of benzene or neutral compounds like that. If I change the buffer concentration, that's equivalent to changing the salt concentration, and we know that there's a slight effect of salt. We just talked about it. It's the Hofmeister salting out coefficient. There will be an effect on a neutral species if you change the salt concentration. But if you keep the salt concentration the same and vary the pH, you're not going to see anything happen to a neutral compound. But you will see all hell break loose for things that can ionize or be protonated. So we're going to start by thinking about simple monoprotic acids and simple monobasic bases. And of course, what we have to consider is these equilibria. Now, the fact of life is that ionic compounds are more water soluble than non-ionic compounds. So when the analyte is in the ionized form, the Bronsted base form, it will be less retained than when it's protonated and has no charge. Conversely, the non-protonated base, electrically neutral, is going to be less water soluble than the protonated base. So as you change pH, you're going to see retention of monocarboxylic acids and monobasic bases change in the opposite direction, because the neutral compound has a different relationship to the ionized compound. Here's a bunch of monoprotic carboxylic acids. This is from a wonderful paper by Chava Horvath some 20 plus years ago. I don't remember what all of these acids are, but I know that that one's benzoic acid and this one's homovinylic acid, and these are related to neurotransmitting compounds like DOPA. You see a lot of crossovers in retention here as pH has changed. So for instance, at this pH right here, the separation of those two compounds is impossible. At this pH, those two compounds are impossible. There's another pair that's impossible as the pHs change between 2 and 4. That's not a big pH range. What you're going to have to do to make this work is find a pH where their retention factors are different. So we really need to understand how the retention factor varies with pH. In my opinion, the simplest way to understand this is in terms of what we call in quantitative analysis courses the alpha fraction. So the alpha HA fraction, that's the fraction of the monocarboxylic acid that's in the HA form, would be the ratio of the concentration of HA at equilibrium to the sum of the HA and A minus concentration at equilibrium. So it's the concentration of the specific form relative to the total. HA plus A minus is the total of all of the Bronsted conjugate. Alpha A minus is simply 1 minus alpha HA, that's easily calculated to be concentration of A minus over the same sum as before. Now it's a very trivial matter to combine a mass balance expression and a Ka expression. If you don't know how to do this, you damn well better learn how to do it. Go back to your quant book. If you didn't get this in quant, go back and ask for your tuition back because you were gypped. But it's easy to show that the alpha HA is the hydrogen ion concentration over H plus the Ka, and the A minus is 1 minus that, and that's going to be Ka over H plus Ka. And what we're going to do is we're going to calculate the average retention by weighting the retention factors of the two forms by the fraction that's in that form. Before I do that, this is a plot. This is a plot of the alpha HA, and this is a plot of the alpha A minus. I'm sure you've seen plots like this before. As we increase the pH, the fraction that is in the protonated state varies from 1 down to 0. The fraction that's in the Bronsted conjugate form varies from 0 to 1. They cross, each is exactly a half when the pH is equal to the pKa. If you remember your titration theory, the pH is equal to the pKa at the half titrated point. So, we're going to take these two fractions and we're going to multiply the retention factor at low pH where it's all protonated by the fraction at a given pH that's protonated, and add to that the retention when you're at a high pH where it's all in the Bronsted conjugate form times alpha A minus at the pH that you're running the chromatogram at. So this is just the alpha fraction average of the two extreme points in the retention curve. If you think about it, this is no different than when you're asked what is the UV spectrum of an acid-base indicator. You got to know the absorbance of the protonated and the absorbance of the unprotonated form, and you weight them by the alpha fraction. This is exactly the same, except we use the retention of the protonated and the retention of the Bronsted conjugate form. Same exact thing. Trivial. And this is what happens. All of the solid lines are monocarboxylic acids. All of the dashed lines are monoprotic amines. You see the solid lines all go down. All the dashed lines go up. The reason they look like this is they pick different values for the KHA and the KA minus for the three different systems, the A, B, and C systems. They assign different values. So this one had a high HA, a high KHA, and a 0 A minus. But the A minus, the K for the A minus doesn't have to be 0. It could be finite. The A minus can have, especially if it's a really organic-y looking compound, really hydrophobic compound, that could be retained in the stationary phase. And the same is true of the bases. Depends on how hydrophobic the protonated form is. This was a clever experiment. Horvath did the chromatography of these acids in 1 molar, I believe it was potassium chloride, and he titrated them in 1 molar potassium chloride, and he measured the pKa's. He measured the pKa by chromatography by fitting the data that he got for the K prime versus pH. And of course, you do the titration experiment, and you all know how to measure pKa's by titrimetry. But that's not bad agreement. That's amazing agreement. The chemistry is the same. It's all simple acid-base chemistry. He even worked out some dicarboxylic acids here. And here's the Ka1 and Ka2 measured each way. Would that life was just I don't really want life to be monocarboxylic and monobasic bases. And certainly biochemistry is not limited to monoacidic species. So let's look at what goes on with dicarboxylic acids and with my favorite case, which are Zwitterions. Anybody remember what a Zwitterion is?
It has a positive and negative charge.
Exactly. It has an acid and it has a base, and you can have it either be protonated or unprotonated or both. And the Zwitterion is the species in the middle. So for instance, let's take is that glycine? No, it's a fair approximation of glycine. That would be the Zwitterion form of glycine. Let me get rid of that. If I work out the math, and it's really quite trivial, these are the alpha fractions of the Zwitterion. But the same math really applies to a dicarboxylic acid or a dibasic base. That would be the alpha HA+. That would be the neutral species, meaning the one that's got a proton on one end and a negative charge on the other end, so its net charge is 0. And then A- would be the fraction where the carboxylate is ionized. You really don't need to know these equations. This one you need to know. So the retention factor is going to be the alpha fraction weighted retention factor for each form. We have something that has 2 protons. If you had 3 protons, something with 2 protons has 3 forms. Something with 3 protons has 4 forms. Something with 4 protons has 5 forms. And a protein. So the pH dependence of a protein is something to behold. But clearly, the pH is going to have a big effect on these different species. Here's the alpha curves for dicarboxylic acids and Zwitterions. This would be the alpha of the H2A, or the alpha of the HA plus, or Zwitterion. This would be the alpha HA minus, or the alpha A if it were Zwitterion. This would be the alpha of the doubly charged, or the alpha of the A minus form if it was Zwitterionic. And the pKa's here are very different. This pKa is a little bigger than 2, and this one looks to be a little bigger than 9. I'm guessing 2.5 and 9.5. And because the pKa's are so different, there's a big pH range where it's almost all Zwitterion. if the pKa's are closer together, this peak first gets narrow, and then as they get real close together, that peak will drop. It won't go up to 1, but you can see it's going up to 1. And this is what plots of the retention factor versus pH of the mobile phase look like. This number refers to the retention factors of the 3 different forms, 10, 5, and 3. And this is a different case. This is for diprotic acid, 10, 2.5. Curve A and C, the pKa's are 4 and 7. And curves B and D, the pKa's are 4 and 5. So the pKa's influence the curves, and the retention factors of the 3 species influence the curves. You can get all kinds of shapes now. Now these are just dicarboxylic acids. Here's a comparison of phthalic acid. That's just dicarboxylic acid of benzene. And here's anthranilic acid, and it's a Zwitterion. The interesting thing about Zwitterions is the neutral form, the one that has a net charge of 0, is actually going to